Hey everybody, it's Jesse with a quick video on the topic of can CrownLink cause desyncs? Now to answer that question, let's talk first about what a desync actually is. Now, Cosmonarchy and the StarCraft Brood War engine underneath it works a little bit like a board game. So in the sense that it's turn-based, not in the sense that you take turns, but rather that the game is divided into turns. Now, unlike a board game, everyone takes their turn at the same time. With our standard implementation, there's 8 turns per second, so a turn represents all the things that happen within 1/8 of a second or 0.125 seconds, right? So within that 0.125 seconds, all of the actions that are taken, all of the different things that happen are collected together in a turn, and then it is exchanged between all of the different peers on the network on the game. Right, so let's say you, for instance, order a unit to move, like this Mason. You're going to order it up to the top of the screen here. What's going to happen is your turn is going to include that move order. And so when the turn is sent between the different players, your turn is going to say move that unit to that location. Perhaps the other player, as you can see in this potential diagram, doesn't have any updates to send. Maybe they didn't click something in that exact 1/8 of a second. However, there is still a turn sent. Right, so the game doesn't progress until everybody's turns are collected. In the case of a 2-player game, until both peers have received the turn from the other peer, the game will not progress till the next turn. And that's actually where you get a little bit of a delay. If you, for instance, haven't received the turn from the other player, you might have a little hiccup, a little delay, a little pause in the game. But in any case, how does this relate to desyncs? Well, keep in mind the game is not sending all of the data about the state back and forth. It's only sending what the commands were, what the actual updates were for that specific turn. So we have this command to send this Mason up to the north. It's just going to send that command, and then the game is simulating that command being acted upon on each of our individual games here. So one thing that can happen is if there's a difference in the logic on how that command is processed, you can actually have the command be processed differently from one peer to the next. And this is actually what causes a desync. Right, so you have that command or that game update, whether it's a damage counter or a random or whatever the case may be, that's synced between those two games. It's interpreted differently by each game, and now the games are on different states. The games are no longer synchronized, right? That's a desync. So how does this affect CrownLink? Well, you might wonder, can network traffic going between two peers ever have a problem that results in a desync? Right? Could we have some data that's missed? Maybe that command to move the Mason was sent to one peer but not the other, and therefore the game state is now desynced. Or perhaps could we have an issue where the command was mangled? Maybe some of the info was wrong, it's sent to a different spot, and now we have a desync. It's a good question, but let's talk about how the game works with its underlying networking in order to understand why this is something that couldn't really happen. First of all, the game uses a library called Storm to manage all of its networking. There you can see the storm.dll sitting next to the starcraft.exe in the base game folder, and that implements a couple of interfaces for sending and receiving data. You have the SPI send, SPI receive. These work a little bit like the loading dock at a warehouse, right? You might have a warehouse that has a couple of loading docks here where you've got a sending and a receiving doorway there. If you're transporting data between two of your warehouses, how do you make sure that what you sent from one warehouse receives at the other warehouse, right? How do you check that? Well, typically in the industry, you would have something called a manifest, and that manifest is going to include information like a shipment number, right? And a shipment number will allow the person receiving the order at the other end to know if they missed one. Right? If they just had shipment number 100, shipment 101 is what's expected next, and now shipment 102 arrives, well, we might have missed one, right? That shipment number lets you figure that out. Then the manifest will also have what's included in the shipment, right? We got 3 widgets, we got 7 sprockets, and if there's any other number or any other items, the person receiving that will know that shipment did not come in correctly. Now it works similarly with StarCraft, right? You have a header on the packet, And the image on the left here is actually directly from the leaked the leaked Storm source code. So this is actual source code that is used in the game. And as you can see, there's a header that has a checksum, has a size value in the bytes, has a sequence, has an acknowledgement sequence, and this performs the same function as the manifest, right? Just like the shipment number could tell you if you missed a shipment, the sequence number and the sequence acknowledgement number tell the game whether it missed a packet, right? That command that was sent by the player to move the mason, it can actually tell if it missed a packet, if there was a turn that was missed, right? And it acknowledges all the turns that it's received from its peer. So they can stay perfectly in sync on the number of packets sent back and forth. Additionally, you have a checksum and a bytes field or size, and this is like the inventory of the manifest. A checksum is basically math that's done on the packet. So you take all of the data that's within the packet, within the message, and you do some kind of mathematical operation to it. Like a simple example would be adding it all together, because bytes can be interpreted as numbers, right? So imagine you add together all of those binary bits, and that will come out with a sum that you can then compare versus, right? And what that shows you is if any of the data is different than when it was sent. Because if a single bit is flipped somewhere in that packet, the checksum will now be off. Now there's more complex ways of doing it than just a sum, just addition, but you get the idea. The checksum shows you if anything has changed in the message to follow. Similarly, bytes is the size of the message, and so when the game is receiving one of these messages, it knows how big it is, so it can tell if it's been truncated or perhaps there's been some additional garbage data appended to the back of it. Whatever the case may be, it knows if that message has been changed or if that message is perhaps the wrong size, or if one has been skipped. Right. And so if we think about our loading dock example, the responsibility for checking the packages that have come in is on the employees at the loading dock. And that's kind of like what we saw in storm.dll, right? The game is actually checking this information to find out if something is wrong with the information that it got from the other game. It's checking if that command is exactly what was sent by the peer. Now, of course, in real life, you wouldn't just rely on the actual manifest from the loading dock. The carrier also has a manifest, right? They don't want to get blamed for something that wasn't their fault, right? So they're going to keep track of what items and what weight, etc., is in their packet, so that they're not going to have any problem delivering that. And it works the same way with CrownLink. So we have our game turn data, which in this case would include that command to move the mason up to a new coordinate, right? So that game turn data is encapsulated in a StarCraft message, which includes a header, a checksum, and a size, right? And so StarCraft can actually tell if anything was changed, if anything was missing, and it can react accordingly. And then that is actually encapsulated in a UDP datagram that's sent using the CrownLink peer-to-peer libjuice protocol, right? So that UDP datagram is sent out the Windows, the Windows operating system's implementation of UDP, and it also has a header with a checksum and a size, right? So Windows knows if anything has been tampered with or is missing, or if there's any problems with that data, right? And so if there's anything wrong with that data, Windows isn't even going to deliver it to StarCraft. And if it does look okay, but maybe there's a missed packet, right? StarCraft is going to be able to tell that from the sequence number, and it's going to be able to request a resend of the missing data. So in effect, CrownLink is like this transparent path between these two computers that are running the game, right? And if there's ever anything wrong with the data that's sent between those users, well, it's going to get trashed, right? That data is going to get completely not processed. It's going to get eliminated, and then there's going to be a request for a resubmit or a resend. So let's look at a demo, right? I'm not expecting you to take my word for it. Let's see if we can't cause a desync with CrownLink. So this is something I recorded a little bit earlier. We'll just watch it together here. This is the source code for CrownLink. And let's play this a little bit faster here. Faster, there we go. Okay, 1.5 speed. All right, so we're going into the juiceagent.cpp file. This is where it is controlled how packets are sent between individual devices. And what we're going to go ahead and add here is a little packet counter to keep track of how many packets are sent between the two peers here. And we're going to try and cause a desync by messing with this data as much as humanly possible, right? When we send that data, we're going to try and mess with it. We're going to try and make it work, or rather we're going to try and make it not work. So here's where we send the data. And this is data coming directly from StarCraft. You can see how simple it is. It's literally just doing a juice send and then it's sending the data, right? There's not a whole lot going on there and not a whole lot that CrownLink is doing, but let's go ahead and change that. So the result of this is, again, every 15th packet, we are randomly changing a value in, and every 20th packet, we are just not sending, right? This should cause a desync if anything can, right, in the network stack. But we just talked about how the game actually can handle this, right? So if we go ahead and zoom forward a little bit here, so we've got a multiplayer game here. We joined it from another computer. We're gonna go ahead and get started here. And as you can see, even though every 15th packet is completely mangled and every 20th packet is dropped, the game is proceeding just fine, right? I can go through here and you can look at the game is working just fine. In fact, we got a little fight going on here. No desync, no problem. Now, if we look at the actual logs, if I pull up the CrownLink error logs here, let me just add some highlighting here so it's easy to see. So what you can see here is our send and receives, right? Our individual packets sent and received. The packet type here is a 2B packet, that's a game packet. And we can actually see right here where we have one that has been missed. So the value E4 there, it's going to be a little hard to see, but maybe you can see that it is in that list of bytes there, it is 1, 2, 3, 4, 5 bytes, and you see how it says E4. That E4 packet was one that was mangled. And what happens is we get an SPI receive message of the type 0C, that's what's highlighted right here. And you can see it says E4 if that fifth character in there, fifth byte in there, that's actually the other side of the connection requesting a resend of that. And you can see right below that we have SPI send again with E4, so it's resending that packet, right? So the game seamlessly resent that packet that was either mangled or lost. And we can look through this log and we find other examples of this, but suffice to say, the game is actually smart enough to handle all of these problems. Even if we completely try and mangle the packet or drop the packet, the game is smart enough to actually fix it. So what can we say in conclusion, right? Now that we've had that demo, what can we say in conclusion? Well, it's not to say that CrownLink is error-free or won't ever have any problems, right? There's definitely errors, there's definitely glitches, there's definitely problems, right? So CrownLink can cause problems, and I'm not saying that it's perfect. However, one thing that I am saying is that you can have confidence that if you receive a desync, if you have a desync, it is 100% of the time not CrownLink's fault in a normal gameplay scenario. Right? Because all CrownLink is doing, again, is sending that data back and forth. And if that data doesn't match up, then it's the game's fault, right? Because it's the same exact thing going in one side and out the other, and the game is discarding any bad packets in between. So hopefully this video helps explain that. Hopefully we get a few less people seeing a desync and swapping between network modes. Oh, let me try something else, I got a desync. You should definitely report desyncs in the CM issues Discord thread, but they're not CrownLink problems, right? CrownLink has other problems, not desyncs. So hopefully that helps. give you a little bit of a peek under the curtain there. If you want me to try harder to cause CrownLink to desync something, I can make it drop every other packet. I can make it swap more than a few bits in the packet. Let me know. I can give that a try if you aren't fully convinced by this video. But in any case, hopefully that gives you hopefully that was at least interesting for you, and have a good one. Bye.